when we have a predicting rule that predicts yes or no outcomes, we would like to quantify how well this rule does its job. And when we quantify it, we use a few numbers, and two of them is sensitivity and specificity. And maybe a little bit more intuitive is the corresponding error types. So the first type of error is when an infected person gets a negative test. So this is error of type 1. And the second error type is when a healthy person is tested positive. So this is error of type 2. Okay. Now the dual concept is sensitivity and specificity. Sensitivity is just the true positive rate, or in other words, percent of the sick people who were correctly identified as such. And if you write it as a conditional probability, it's just conditional probability that the person gets a positive test, given that the person is actually sick. And specificity is the true negative rate, or percent of the negatives correctly identified as such. And again, if you write this conditional probability, it's probability that the person was tested negative, given that the person is healthy. Here I'm using those notations. T bar stands for t equals to 0, and d bar stands for d equals to 0. Bar means not, negation. So t bar means not tested positive, and d bar means not healthy person. Okay, and here's the connection between the sensitivity and the error types. So the first error type is just 1 minus sensitivity, or another word for it is the false negative rate. And the second error type is just 1 minus specificity, which is also called false negative rate. Okay, and now when we combine all those things together, so error types or negative rates, false negative rates and false positive rates are bad things. So we want them to be as low as possible. On the other hand, we want the accuracy or the good things to be as high as possible, and we have, so overall accuracy can be measured as the number of correct answers divided by n, but this number doesn't give us the full picture because we don't really know what type of errors we made. So when you look at the accuracy, you don't really have a good idea, or don't have any idea whether most of the mistakes were made to incorrectly labeling sick people or incorrectly labeling healthy people. And in real life, it's important what type of mistakes you make, because in real life, for example, it's much more costly to label a sick person as healthy rather than labeling healthy person as sick. If you label a healthy person as a sick person, person gets a positive test, you can redo test, or you can re-examine it, and eventually you will find the truth. Eventually you'll find out that the person is healthy. On the other hand, if you test it negatively and you have a sick person, then you might have missed an opportunity to intervene, to apply some treatment and save the person. So a person leaves with assumption that there's no problem, while there is a problem, and so the cost of the mistake is much more costlier in the case when you missed a disease rather than incorrectly labeling a healthy person as a sick person. Okay, so accuracy is one way to measure the predictive rule, the accuracy of the predictive rule, the quality of the predictive rule, but it doesn't tell the full story. So in order to tell the full story, we need to use what is called confusion matrix. Confusion matrix actually specifies 4 numbers. So true positive rate, and true negative rate. So how many people were identified correctly as sick people, and how many healthy people were correctly identified. And then 2 types of bad results. So false negative rates. So those are the sick people that we missed, proportion of the sick people that were not identified by the test, And false positive rate is the proportion of the people who were tested positive while being healthy.